This equation defines the relationship between the physical structure of a component and its capacity to store electric charge. To understand how a circuit actually operates in the real world, we have to look at how these values change over time. We do that by taking the mathematical derivative of the entire equation. When we apply the calculus product rule, current is revealed as two separate processes, the change in voltage and the change in physical capacitance. But in standard physics textbooks, component sizes are assumed fixed, making capacitance changes irrelevant. That simplification works for rigid, stationary circuits, but it fails to account for any system where the internal geometry is deliberately designed to physically shift. Alessandro Volta's Electrophorus is one of those systems. When Volta announced this instrument in 1775, he claimed it could yield an essentially unlimited number of charges from a single initial charge. The device consists of a metal plate and a charged block of resin. Simply by placing the plate down, then touching it, and picking it up, the operator generates thousands of volts of electrical potential. Because the original charge on the resin is never consumed, the device appears to generate electricity without a clear energy source. The mechanism actually functions by exploiting that second term of our expanded calculus equation. Consider the standard textbook case, a rigid condenser, such as an underground high-potential cable. In this setup, the metal and insulation are locked in place. The physical volume available to hold electrons is a constant value, which means the change in capacity is zero. Because the geometry cannot expand or contract, the only way to alter the voltage is to physically move electrons out of the cable. As the electrons flow out of the cable as current, the electrical pressure drops. This is similar to a steel tank filled with compressed air. To lower the pressure inside, the air must be vented out of the fixed space. In modern electronics, changing the voltage is almost always a result of moving charges in or out of a static space. The Electrophorus functions by reversing those priorities. It begins with a base of resin that has been rubbed with fur, giving it a dense, permanent layer of negative charge. A neutral metal plate is placed on top of this charged resin, making contact only at microscopic surface peaks. The negative field from the resin repels the free electrons inside the metal, driving them toward the top surface of the plate. The operator then presses a finger against the top of the metal plate. This provides a path to the earth, allowing those repelled electrons to escape through the operator's body. Once the finger is removed, the plate is left with a net positive charge. These charges are held tightly by the negative base pulling on them from below. This creates a closed system with a trapped, isolated charge that cannot flow anywhere else. The operator then performs the second mechanical action, lifting the metal plate by its insulating handle. Because the plate is now surrounded by air, no electrons can leave or enter the metal. Since the quantity of charge is physically locked, the current term in our derivative equation becomes zero. With the current eliminated, the two remaining terms, the changing voltage and the changing capacity, must balance each other. As the plate is lifted from the base, the physical capacitance drops sharply. To maintain the equation's balance, the potential difference reacts. The voltage spikes into the thousands. This is similar to a flexible tank being squeezed. Reducing the volume forces the existing fluid to a much higher pressure. That voltage is the direct result of the operator's physical work being converted into electrical potential. The underground cable and the Electrophorus represent two halves of the same physical law. One relies on a changing charge in a fixed space, while the other forces a fixed charge into a changing space. Lifting the plate requires overcoming the intense electrostatic attraction between the positive and negative charges. Voltage, in this context, is a measure of the work required to pull those charges apart. This action literally pumps the field lines, stretching them across a larger volume of space. That energy is provided entirely by the physical effort of the person lifting the plate. When that immense potential energy finally bridges the insulating air gap, the result is a massive high-voltage spark. Because the original charge on the resin base is never consumed, the process can be repeated, as long as the operator has the strength to keep lifting the plate. This same principle of variable capacity drives larger devices, such as the Wimshurst machine and modern electrostatic generators. The calculus product rule describes the literal mechanical work required to move these components. Understanding electricity requires looking beyond static symbols to the physical mechanical tug-of-war happening between electric fields.